Hello everyone, this is Mr. Tanner, and for this set of notes, we're going to be looking at gravity and how it interacts with planetary motion. So how gravity drives planetary motion. And more specifically, we're going to be looking at how our thoughts on planetary motion has changed throughout time as we look from pre-Copernicus all the way through Einstein's ideas of general relativity. Looking at the table of contents, we're going to start with the pre-Copernicus models of planetary motion. This would be when the Earth was thought of as being the center of the solar system, a geocentric model. Then we'll look at Copernicus, who introduced publicly the heliocentric model of a solar system. Then we'll move on to Kepler's laws of motion, Newton's law of universal gravitation, and then finally we'll look at Einstein's ideas or theories of general relativity and how they explain how gravity works. Starting with that pre-Copernican ideas of a geocentric model of the solar system. And what this means is that prior to Copernicus publishing his works, we as humans largely believed the Earth was the center of the solar system, and the sun and all of the planets orbited the Earth. And it's not fair to just say that that was really silly, because from our perspective, what we might call a reference frame standing on Earth, it certainly looks like the sun goes around the Earth and all of the planets go around the Earth. And it doesn't feel like we're moving very quickly through space. But when Earth was the center of the solar system, the planets in the night sky would sometimes change direction. So sometimes they'd be moving one direction across the sky, and then for a few days or for a few weeks, they would backtrack and move the other direction before continuing to move the original direction. And it wasn't like this was random. These humans, these scientists at the time could calculate exactly how the planets were moving. They could make predictions. They knew where the planets would be. They just believed they traveled in what is called epicycles. So they thought the planets traveled in epicycles. What an epicycle really is just a circle rolling on another circle. So if this is the Earth here in the center of the solar system, and we have a planet orbiting around it, and usually the planets would be thought of as orbiting counterclockwise, so I might show this moving in the other direction. But instead of the planet just staying on a nice circular orbit, the planet is rolling on a circle around that circle, which traces this kind of spiral shape. And they called that, since it's a circle rolling on another circle, an epicycle. And I will show you in just a second, using the solar system scope simulation, what that would look like. Because in that simulation, you can actually set the Earth as the focal point of the solar system and watch everything orbit around it. And sure enough, you can see these planets moving in their epicycles. Next, we're going to look at the Copernican model, which is the heliocentric model of the solar system. And this didn't make it didn't make the fact that we could track planets for the first time, because we could already track planets, but the math of Copernicus had the planets all moving in circular orbits. So that the reason that this model caught on, the heliocentric model, is that it eliminated that need for epicycles to explain planetary motion. Copernicus realized that if you put the sun at the center of the solar system, then the known planets orbit in what he thought would be perfect circles around the planet. So this is why the heliocentric model caught on. We still consider the sun to be the center of the solar system because it simplifies the orbits of the planets. Although where Copernicus was wrong was in thinking that the planets are orbiting the sun in perfectly circular orbits, which our next scientist would show was false. So that brings us to Johannes Kepler. And Kepler introduced 3 laws of planetary motion. And the first law was that planets move in elliptical orbits. Now, the difference between a circle and an ellipse is that in a circle, at the center of that circle, we would have what we call a focus. That is the very center of the circle. And then every single distance around that focus is equal, creating a perfect circle. So this would be a circular orbit. In an elliptical orbit, an ellipse has two focuses. So it might have a focus here and a focus here, and one of those focuses was the sun. The other one didn't actually have anything at it, but this is just what explains the shape of an ellipse. And the distance from one focus to the other would be, like from the planet to the other would be the same. So if you had a planet orbiting this is a very exaggerated ellipse. The planets move much closer to circles than this, but you end up with an oval-shaped elliptical orbit. So at some points, this planet is closer to the sun than at other times. And we would call this closest point the perihelion. So the perihelion, that means near the sun, is the point that the planet is closest to the sun. And the point that the planet is farthest from the sun is the aphelion. The second law, or second of Kepler's laws of planetary motion, is that planets travel across the same area of space in the same amount of time. And this is confusing to hear, but if you draw it out, I think it makes a lot more sense. So again, we're going to set the sun right here, and we're going to draw a highly elliptical orbit. This is much more dramatic than the planets actually do. But this planet, we'll have a planet here, is orbiting counterclockwise around the sun. And we're going to just pretend that the areas we trace out are triangles to make the math easier. They're not triangles, they're arcs. The math on calculating an arc is a bit more complicated, but the same idea will hold if we just pretend these are triangles. So we're going to draw a triangle going towards the aphelion, the point that we're furthest away from the sun. And we're going to just fill that in because that represents the area of that triangle. We know it's not actually a triangle, but the same idea will hold. And let's pretend that this tall, skinny triangle has a height that is equal to 10 units, whatever that unit is, and a width that is equal to 2 units. Well, we know that area equals 1/2 base times height. So that's 10 times 2 divided by 2. These cancel out, the 2's cancel out, and we just get an area of 10 units. So the area of this shaded place is 10 units. Now on the other side, towards the perihelion, we're going to draw a much wider but shorter triangle. It becomes more obvious that this is arc-shaped here, but we can then do the same math. Let's say that this short, wide triangle has a height that is equal to 4 units and a base that is equal to 5 units. Well, area equals base times height over 2, which equals 5 times 4 over 2. And if you do 5 times 4 is 20, 20 divided by 2 equals 10. This has the exact same area. So the first part of Kepler's law is the planets are traveling across the same area of space. Well, this triangle here has the same area as this triangle here. And then Kepler's law states that the second law of planetary motion states that they do that in the same amount of time. So let's say for this planet, each distance represents 1 month. So as we go down here, this is also 1 month. And what this matters is when we're near the aphelion, that point that is really far away from the sun, it's covering a distance that is 2 units in a month. So it's covering, 1 unit of distance every 15 days or something like that. When it's near the perihelion, the point that's closest to the sun, the planet is traversing a distance of 5 units, also in 1 month. So now it's going a unit of distance every 6 days instead of every 15 days. So what this law states, mathematically, it's telling us that as planets are closer to the sun, they move faster. And when planets are further from the sun, they slow down. So this is important to understand. But this idea that says planets travel across the same area of space in the same amount of time, what that ends up meaning is that when planets are closer to the sun, they move faster than when they are further away from the sun. That's Kepler's second law of planetary motion. Kepler's third law of planetary motion just states, and I'm simplifying this because he does some math involved here, but this is what the math tells us. It says that the orbital period of a planet directly relates to the size of that orbit. And all this means is if the orbit is like smaller, the planet's going to orbit much more quickly. If the orbit is larger, it's going to orbit much more slowly. And what Kepler found was that if you compare like the maximum axis of the orbit, that distance that would go all the way across the maximum axis, and then you compared that distance to the orbital time, and then you like would square one of those numbers and cube the other, all of these planets and that of the known planets gave out the exact same ratio. So you don't need to understand the math of that. All I want you to know is that the time it takes for a planet to orbit the sun is directly related to how large that orbit is. There's not like some planets further away decide to move quicker for some reason. All of their orbital speeds depend directly on the size of that orbit. I think the most important two laws here are that planets move in elliptical orbits, so the first law of planetary motion and the second law. When you're closer to the sun, they travel faster than when you're further away from the sun. Kepler, though, couldn't figure out a mathematical equation that would explain why planets move faster when they're closer to the sun. So he knew that they did through careful observation. He knew that the planets were ellipses through careful observation, but he could never put a mathematical equation to why they moved faster. And in fact, no one could until our next scientist on the list, which will be Newton. Sorry, before we get to Newton, actually, here is two other looks at Kepler's first and second law. So we just have the sun at one focus, nothing at the other, as the planet orbits in an ellipse. That would represent the first law of planetary motion. And then we see the smaller area, or the smaller width area. The areas are the same. A1 is equal to A2, but the planets are traversing the same area in the same amount of time, which means the planet is speeding up near that perihelion and slowing down near the aphelion. Now we'll look at Newton. So what Newton was able to figure out through some very, very advanced math and calculus, which is a type of math that Newton actually invented, was the mathematical equation that would explain how the force of gravity worked, that would explain why planets move faster when they're closer to the sun and slow down when they're further from the sun. And this is Newton's law of universal gravitation. And what this law states that any two objects with mass, so we have an object here, mass, that has a mass of mass 1, and then we have an object here whose mass is just m2. And what Newton knew is that the force of mass 1 is the exact same as the force of gravity on mass 2. They pull on each other with the same amount of force. And this is really strange because it would mean that I pull on the Earth, if I'm m2, the smaller mass, I pull on the Earth with the same amount of force that the Earth pulls on me, which another way of thinking of that is perhaps even more strange, that on Earth's gravity, I weigh 200 pounds, but on my gravity, the Earth only weighs 200 pounds as well. So if we were to put a scale on me, the Earth would weigh 200 pounds sitting on me. Those forces become equal. So what Newton realized for gravity is that both the masses matter. So we have to multiply the first mass times the second mass. That means if the mass increases, the amount of gravity also increases. The reason why planets slow down further away from the sun and speed up closer to the sun is because that distance between them, this distance represented by the letter r, if you square that distance, that changes the gravity as well. So if, like, just working some really simple, this idea, like if planets are further apart, the force of gravity is actually weaker, which is why the planet is slowing down. And when these two objects are closer together, this number becomes smaller. We're dividing by a smaller number. The force of gravity is larger. So when these two objects are closer together, their gravitational force is much larger than when they're further apart. So Newton realized that the force of gravity depends on both of the masses and the distance between the two. As mass increases, the force of gravity increases. And as the distance increases, the force of gravity decreases. This g here is just called the gravitational constant, and Newton actually never figured out what that number was. He knew there needed to be a gravitational constant, but it took another scientist and a lot more observations to actually figure out what this number was. And it's just a really small number because Newton realized the forces that he was calculating only using this were way too big. So we knew there had to be something multiplied to make it smaller. It's just much, much smaller than 1. So you don't need to know that. We're not going to be doing the math on this. What you do need to understand is that under Newton's law of universal gravitation, as mass increases, the force of gravity increases. And as distance increases, the force of gravity decreases. And that brings us to our final scientist on this journey of gravity and planetary motion. And it is the strangest one, but all experimental evidence shows that this is also the correct explanation. And that brings us to Einstein. So Albert Einstein, under his theory of general relativity, so this is the theory of general relativity, Einstein stated that gravity is not a force at all. There is nothing that is pulling me down to the earth. Instead, or there is nothing that is pulling the planets around the sun. There is no force. Instead, what's happening is that matter bends space-time. So this grid that we're looking at on this image represents space-time. This object here, which has lots of mass, is bending space-time. So matter bends space-time. The larger the mass, the more that space-time will curve. So it's creating these curves. And that means that any object that is traveling through this bent space-time will curve even though it's still traveling in a straight line. And this is very strange to think about, but we can kind of view this. If I start and I say I'm traveling in a straight line going from one corner to the next corner before before matter is bending this space-time, we're just going to go from corner to corner of each grid. If I keep doing that, my line curves a little bit. And we can trace another line here, corner to corner. It bends a bit less. If we do one more, you can almost see now that it was hiding behind the object for a little bit. It actually would curve behind the object as we trace corner to corner. I think I actually lost it. I think it would come back here. So these objects are traveling in straight lines, but they appear to be curved due to the bending of space-time. So if something was traveling at the right speed and it was following this curved line, or the straight curve all the way around, it would just start orbiting a planet because of the curvature of space-time. So objects have to follow this curve. And this sounds really strange, but there's some things that are explained by gravity, or Einstein's ideas that gravity is not a force, it's just a bending of space-time, that Newton's law can't explain. For example, Einstein, using this math, predicted that light should bend under gravity. Light has no mass. Under Newton's laws, the only thing that would cause light to bend is the fact that light has momentum. So momentum actually can be and is an energy, and energy can be impacted by gravity as well. But Newton's laws show that light should barely bend at all due to gravity. And what Einstein said is that, well, light's going to bend from gravity just like anything else. It's traveling faster, so it'll be less impacted. But since it's space that's curving, light's still traveling in a straight line as it curves. So in his theory of general relativity, he put out a proof. And he said the light behind our sun, which is a huge mass, the sun is a huge mass, it should really, really bend space-time. The stars behind it should be bent. And he did the math to say exactly how much the stars behind that should be bent. And the next time that there was a solar eclipse that blocked the brightness of the sun so scientists could actually see the stars behind the sun, or that would normally, the sun normally too bright to see, they looked at the known position of the stars, and then they looked at how much the light was bending, so where they appeared to be, and Einstein was exactly correct. His prediction was perfect. The light bent exactly as much as he predicted. And there's been some other experiments that every time we test Einstein's theory of general relativity, he is correct. And there's going to be a few videos that I'm going to have you watch that will help explain this, but we are very confident at this point that Einstein's theory of general relativity is correct and that gravity is not a force. It is just a curvature of space-time, and things follow straight line paths through that curvature of space-time. The video should help this make sense, but the key takeaways from Einstein's general relativity for our class: know that gravity is not a force. So the key takeaway here is gravity is not a force. It's just that matter bends space-time, creating those curves. More mass equals more curve, and then objects must follow the curves in space-time. So we're not going to do any math here. I'm not going to ask that you fully wrap your head around this because I can't fully wrap my brain around these ideas. They get truly bizarre, but every experiment shows they are correct, and I just want you to have these 4 bullet points in mind. Gravity is not a force. Matter bends space-time, creating curved space-time. The larger the mass, the more that space-time curves. And then objects must follow that curve in space-time as they pass through it. Make sure you take the time to watch the YouTube videos that are going to be linked next to these notes. And thanks for watching. Please let me know if you have any questions.